This is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So, today we will discuss the reliability of bivariate econometric modeling. So, in the last class we have discussed the entire setup of bivariate econometric modeling, where the problem boundary is with respect to two variables. So, we have discussed the details about the estimation of alpha head and beta heads. So, after getting the estimated value of alpha head and beta heads, so then our problem setup is completely different so far as a forecasting or policy implication is concerned. So, let me highlight what is the means last class discussion. So, for bivariate models with respect to y and x, y equal to alpha plus beta x, and we have to introduce the error terms u, and the estimated model equal to y head equal to alpha head plus beta head x, okay, and where alpha head equal to y minus y bar minus beta head x bars, and beta head equal to summation x y by summation x squares, where x equal to x minus x bar and y equal to y minus y bar. This was our last class discussions. Okay. But you know the movement from the first equation to second equation, where the estimated models we have described y head equal to alpha head plus beta head x. So, we have applied the technique called as a OLS techniques. Of course, there are several techniques like ordinary least square methods, generalized least square method, weighted least square methods, and maximum likelihood estimator. So, here we start with the OLS technique, that is ordinary least square methods, because it is very simple technique, easy to understand and easy to apply. That is how we start with the OLS technique, then we subsequently move to GLS techniques, OLS techniques, and MLE technique, where we need to have, because some of the problems it is very difficult to handle through OLS techniques. So, that is how we have to apply the other techniques like GLS, WS, and maximum likelihood estimate. But in the last class we have little bit problem regarding the OLS restrictions. So, before you applying OLS technique, then obviously we will get the estimated model, but the application of OLS is based on certain assumptions. So, before we check the reliability part of the models, so let me first highlight the assumption related to OLS technique, because which last class we have not discussed details. So, we have to little bit finish about this particular component, because the main problems main problems we will derive from this particular assumptions, because that is the starting point of econometric modeling. So, you see here. So, what are the assumptions regarding this bivariate modeling? So, that is our last class discussion. So, for this particular models y equal to alpha plus beta x plus u. So, we have three parts, this is one part, this is another part, and this is another. This is called as a total variation, this is explained variation, this is unexplained variations. Okay. So, now assumption related to this particular component, and this particular component, and also overall fitness of this particular models. So, the first standard assumption is that model must be linear in parameters. Okay. Linear in parameters. So, what we have already mentioned here. So, here alpha beta are represented in the form of linear, and that too you can say without any problem. So, linear in parameters. Second assumption is that x should be your independent variable should be non-stochastic. Okay. This should be non-stochastic. Okay. So, third item related to the error component. So, what we have discussed last class, mean of error term should be equal to 0. Then fourth assumption is the variance of error term should be equal to unit, that is sigma square u, and fifth assumption is that covariance of u I u j should be equal to 0. Okay. So, here this variance of u means it is nothing but covariance of u I u j is equal to sigma square u, provided I equal to j. If I not equal to j, then this will come down to this stage. Okay. So, now this particular structure is called as a homoscedasticity. If the variance of error term is exactly equal to 1, or constant, or you can say unique, this particular presentation is called as a homoscedasticity issue. So, now if that is not the case, then this problem called as a heteroscedasticity, and that is the serious problem under econometric modeling. We have a special component on heteroscedasticity. We will discuss detail about that particular issue. If there is heteroscedasticity, how to detect it and how to solve this particular component. Until unless you solve that particular component, this model, estimated model, cannot be used for forecasting. Okay. So, then covariance of ui and uj. Covariance of ui uj should be equal to 0. Okay. If it is not equal to 0, then there is a problem called as a autocorrelation, or sometimes it is otherwise called as a serial correlation. So, now if we have estimated models, then of course, with the help of estimated model we will get the error terms. So, now once we have error term, we will create several other variables related to error terms like u1, u2, u3. So, now we have to track the relationship between u1, u2, u3 like this. So, if this relationship by default a cross correlation if not equal to 0, then it will lead to serial correlation. For instance, like this, we have u1, u2 up to un. So, this side u1, u2 up to un. Okay. So, now this is we will correlate with u11, u12, u1n, similarly u21, u22, u2n. Okay. So, un1 up to unn. Okay. So, now this particular problem is called as a homoscedasticity and heteroscedasticity issue. Okay. This particular problem is called as a homoscedasticity or heteroscedasticity problem. If that is if all these other items like this these particular diagonals, these particulars this is called as a off diagonals and on diagonals, these are should be equal to 0. If that is not the case, then this particular problem is called as a serial correlation and autocorrelation. It has a serious problem again in the case of modeling, particularly econometric modeling. So, when there is a serial correlation, obviously, when we will go for any typical problem or any estimated model, there will be definitely autocorrelations. There is a standard techniques are there, standard statistics are there to know the exact value of autocorrelation or serial correlation. There is a certain limits. If it will cross that limits, that means upper limit or lower limit, then it will be problem for estimated model. So, we have to find out how that particular problem can be solved and that model can be used for forecasting. So, this particular structure is called as a autocorrelation issue. Okay. Similarly, this is fifth standard assumptions. Then there is another assumption called as a this is sixth assumption. Sixth assumption related to covariance of u and x should be equal to 0, because our model is equal to y is a function of x and u. So, there are three variables. We start with the 2 variable initially, but ultimately we will get a variables called as a u. Okay. So, that is the difference between y minus y hat, that is estimated model. Okay. Covariance of u x must be equal to 0. Otherwise, it will create problem. So, I will detail discuss next items. So, covariance upon xi or xj is equal to 0. In fact, this xi xj is not actual problem in bivariate model. So, when we will go for multivariate model, then one of the standard constant is that there are multiple number of independent variables like x1, x2, x3 like this. So, now all these independent variables should be independent. Okay, means the relationship between all these variables should be independent. There should not be any again association between these independent variables. If there is such problem, then it is called as a multicollinearity issue. So, we will discuss detail when we will go for multivariate modeling, because we are in the bivariate models and this particular problem may not be there, means it should not be there in the case of bivariate models. So, that is how there is a covariance between u and x. Now, since u is in the right side of this particular equation, obviously, there are 2 variables x and u. So, now if we will integrate with this multicollinearity issue, x and y should be totally independent. That means there should not be any association between x and u. Okay. If it is there, then it will be problem. So, next, so now if we integrate this all these equation in structure with respect to error term, then error term should be followed by normal distribution, 0 mean and unit standard deviations. Okay. 0 mean and unit standard variance. This is the most important one for this particular econometric modeling. Okay. So, then ninth, there should be variation on x, there should be variation on x. Of course, if there is variation on x, then there should be variation on y. For instance, we have y series and we have x series, forget about y in the meantime. So, now for every y there is x items. So, now if the x items are very much similar, then obviously we will get our model cannot be better fitted. For instance, for every y the x values are 2 2 2 2 say or 5 5 5 say, then obviously there is no such variation. So, in this particular context this model cannot be better fitted. So, this is by default we have to replace it, otherwise you cannot get a best fitted model. These are the inspection before you go for, you can say, estimated models. So, because to get the estimated model you have to put lots of labor and efforts. So, after that if the model is not reliable, then obviously you have to redesign and re-estimate to get again better fitted model. But there are certain clues before you go for estimation. So, you have to clarify all these details, and one of such clue is like this: there should be variation on both y and x, but x is very important here because x influence y only. So, there should be some kind of variability in x. Okay. So, this is another assumption related to variance of x, and model must be correctly specified. Model must be correctly specified. Model must be correctly specified. What is mean that? For instance, we are just representing y equal to alpha plus beta x. Okay. So, there are many ways we can represent this a particular relationship between y and x. For instance, we can also write y equal to alpha plus beta to the power x, or we can write y equal to alpha beta by x like this, or we can also write y equal to alpha plus beta x squares plus gamma x like this. So, there are many ways we can represent the relationship between y and x, but for a particular problem or particular instance, every equation may not be very fitted for the econometric modeling. So, we like to know what is the best mathematical relationship we have to use to get the best fitted models. So, for that you have to do lots of homework and you have to test. There are certain procedure of test, or graphically you can plot it, and you like to know what is the exact relation, whether it is a linear one or non-linear one, then accordingly you have to proceed further. In fact, if it is a non-linear one, then it may be very complex problem. So, what you have to do in that linear setup, you have to first transport to the linear format by using various transformation rule. There are various transformation rule through which you can transfer the non-linear problem to linear one. Then you have to go for estimation. So, if you do not go for transformation, then it will create lots of problem again, and means that typically it is problem with the OLS technique. Okay. So, you must be very careful about this. Okay. Then next is number of observations. Number of observations should be greater than to number of variables. Number of observations should be greater than to number of variables. For instance, you see this particular problem for bivariate econometric, it is not a serious issue, because we have two variables only. So, obviously, most of the problems is more than two, you will get more than two sample. So, if it is more than two samples, then obviously there is no issue at all. But when there is a multivariate problem where the problem setup consists of, you can say, so many variables like say 10, 20 or 30 or 100, then that time sample size is a very typical issue. So, you have to be very careful how many variables you must be putting in the system and how many observations are there. So, by default it should be whatever variables you are using in a particular system, your number of sample size should be 5 times than that. So, that means, if the variables are 5 in numbers in a particular system or in a particular modeling setup, then obviously sample size at least should be 5 into 5. So, that means at least 25, but 25 is also very small one. By standard rule, your sample size should be greater than to 30. If it is greater than to means 32 exactly. If it is greater than to 32, then obviously there is a, you can say, we have two different sample structures, small sample and large samples. So, minimum number of sample must be greater than to 32 for a particular problem, whether it is a bivariate or multivariate. And if it is a multivariate, then obviously then there is a second criteria. So, that means the second criteria is number of variables and your sample size should be multiple to 5. So, now if it is 10 variables, then obviously sample size should be at least 50. If it is less than that, then there is a problem of modeling or estimation process. So, if it is more than that, then no doubt about it, the model accuracy is very high when the sample size is very high. The model will be less accurate if the sample size is very small. So, that is how you have to always go for higher and higher sample size. So, that the model accuracy will be very perfect. So, that is how the reliability part is concerned, because the reliability part, the objective of reliability part just to check whether the estimated model can be used for forecasting or can be we call it that it is a best fitted model. So, that for that we have different test structures. By this process of test, we like to say we like to be in a position to say that this particular model can be used for forecasting, or you can say policy use. So, this is a 11th assumption. So, it is where number of observation greater than to number of variables. Then last but not the least, then relation should be very identify one. So, relationship should be properly identify. Okay. For instance, you see here this particular problem for two variable model, it is not a issue, but when you will go for multivariate models, particularly there is we have a component called as a simultaneous equation modeling or structural equation modeling. In that context, you know, model identification is very serious issue. If you do not identify properly that model, then the process of estimation or its interpretation or reliability will be get affected. So, what you have to do first means you must have a very sound knowledge, that is theoretical knowledge, before you go for you know, fitting the relationships. So, because so far as the interpretation part is concerned, so the theoretical knowledge or theoretical background will give you lots of, you know, ideas how to interpret this particular model, or you know, when you will go for forecasting issue. So, these are the standard assumptions through which OLS technique is practically feasible. If these assumptions are on other way around, then obviously this particular technique is you can say the model you will get through this particular technique cannot be used for forecastings, or you cannot build for any use, because it will give you wrong signals, or you can say wrong indications. So, now what is the best idea is, so when we have a model, so y equal to alpha plus beta x, then we have received the models called as a y hat equal to alpha hat plus beta hat x. So, now we have two standard estimators. So, this is called as alpha estimators and beta estimators. You know, this particular estimator should follow certain you know, principles. So, there are certain principles behind this particular estimators. This particular you know, principles is called as represented as a the term called as a BLUE, best linear unbiased estimators. So, that means whatever estimators we are receiving, that is alpha hat and beta hat, that should be best, that should be linear one, that should be unbiased ones. Okay. So, now you see here what is linear. So, linear means it is a linear combination of variable. For instance, x bar is nothing but summation x I divided by n. Okay. So, that means 1 by n 1 into x 1 plus 1 by n 2 plus into x 2 into x 2. So, 1 by n n you know, so n 3 x 3 like this. So, these are all linear combination of x. So, what I like to say that whatever estimators value we have received alpha and beta hat, so it should be linear in nature. So, so that the you know, the theorem can be meaningful. So, that is how it is called as a best linear. With the classical linear regression models, the estimators what we have received by the process of estimation should be linear, unbiased, and you can say it must have a minimum variance. So, what is that minimum variance? So, before that you must have linear in natures, then second, then there is called as a minimum variance, okay, or you say first start with unbiasedness. Unbiased net means what is first bias? Bias means the difference between expected value of you can say, let us say we start with beta parameter only. So, estimated beta head should equal to beta. So, this is true beta. Okay. So, now if the estimated beta is exactly equal to true beta, so there is no gap at all, but we are expecting something, but actually something, that gap should be very minimum. If that gap should be high, then obviously it will create lots of problems. So, that means for every problem whatever estimators we are receiving, so that should be unbiased in nature. That means the estimated value should be exactly equal to truthful. There should not be drastic difference between the as long as the difference is increasing, then the model accuracy will be get affected. Okay. So, this should be taken care. So, okay. So, this is second properties of this particular estimator. Third is a minimum variance. Third is a minimum variance. Minimum variance. So, what is minimum variance? Now, minimum variance is you have to find out variance of beta head is should be less than equal to variance of another estimator, say beta stars. Okay. So, that means whatever estimator we have received, that should be minimum variance. You see, variance is an indicator through which we can judge the accuracy of a particular theme or particular item. If the variance is very high, then obviously that model can be, you can say, cannot be considered as the best fitted model. So, just like we have discussed details in the univariate data setup, where this particular component is called as a dispersion issue. Okay. So, that means the variation from the center point should not be so drastically high. So, it should be uniformly distributed, and whatever the variance we have received, that should be the minimum one. If it is a minimum one, then the model can be treated as the best fitted one. If it is not minimum, then obviously it will get affected. So, variance should be at the lower level. Then fourth one is it should be consistent. Okay. Consistent means it is integration of both minimum variance properties and unbiasedness property. That means, so E beta for estimated beta head. So, E beta head should be equal to beta, and variance of beta should be less than to another variance say beta star. So, when we will go for unbiasedness property only, then there is no link with minimum variance, but when we will go for minimum variance, then there is no point to go for, you can say, unbiasedness property. So, that means there should be you can say two things are completely different, but as far as the consistency property is concerned, it is the integration of both unbiasedness property and minimum. So, unbiased property is that expected estimated beta value is equal to true value, that is not beta head, in fact that is beta only. So, E beta head equal to beta, and variance of beta head should be less than to another variance of another estimators. So, now if that is the case, then this particular theorem is called as a BLUE, best linear unbiased estimators. So, now every model has to be tested with respect to all these indicators. These are all called as a, means these are, we are assuming that these are the indicators through which we judge the reliability of the particular models. If whatever estimator we have received, that should be taken care with respect to all these indicators. If these indicators are going on the right track, then the model accuracy will be high, and we can say that model is a reliable one. So, now we have to know what is exactly this reliability part of this modeling. Okay. So, this reliability part of this modeling basically we see here. So, what is exactly the proper setup here? So, now the model is like this, y equal to alpha plus beta x plus u, all right. So, we are getting y head equal to alpha head plus beta head x. Okay. So, now so far as the reliability is concerned, so the we have to integrate so many things. Okay. So, because we like to know whether this alpha head and beta head are, you can say, a reliable one. So, that is with respect to this particular theorem, BLUE, best linear unbiased estimator. So, that means alpha head and beta head has to be checked, so that the theorem can be satisfied. Okay. So, that means the properties of all these estimators should be as per the rules or principle of this econometric modeling. So, that is what we call it the best linear and unbiased and obviously it will go by minimum variance and consistent property. So, now how do you go for that? When we will get the estimated models, then basically the estimated model will be represented by like this. This is followed by variance of alpha heads, okay, variance of alpha head, and with respect to beta head we will receive variance of beta heads. So, our standard assumption is that variance of alpha head should be very low and variance of beta head should be very low. So, with respect to variance of alpha and variance of beta head, we like to receive the standard error of alpha head and standard error of beta head. So, which is derived through variance of alpha head, okay, which is derived through variance of alpha head. Then there is a term called as a then we have to apply the statistics actually to check whether this particular parameter is statistically significant or not. Okay. So, now to know the statistical significance of this particular parameter, that is what another part of the reliability. It is not like that whatever estimator we have received, that is just follow the principle of blue. In the same times this particular item should be statistically significant, and for that we have lots of test statistics, okay, like T test, F test, Z test, like this. So, now for this particular standard problem, so we usually take the help of T statistic and F statistic, and for this particular angle, so means so far as the significance of the alpha head and beta head is concerned, we have to apply the T statistic, and through which we like to make a judgment whether this particular parameter is statistically significant or not. If it is statistically significant, then obviously this particular model can be considered. If these parameters are not statistically significant, then it will be problem, definitely. But here in this particular bivariate setup, so we have only two items, okay, so that is alpha head and beta heads. But when we will go for multivariate model, there are several betas like beta 1, beta 2, beta 3. Alpha is just supporting component, that is represented as a intercept constant items, and there is a slope items. These slope items are, you can say, beta 1, beta 2, beta 3, like this, and constant term we call it the intercept. This is what we we can get the supporting factor through which you have to start this issue like this, So, this particular representation is like this is alpha head, this is alpha head, and through which you have to start the y head component, that is nothing but this particular item alpha head and beta head x. So, now this side is x axis and this side is y axis. So, now you like to assume that this is particularly estimated model, in between there is a true value, okay, these are the true values. So, we like to know how the best fitted line can be derived through these true values or true points, because it should be by default, or you can say by inspection it should be in the middle of all these points. So, the way you have to design it, so that the path will be in between the two, so that the model accuracy will be very high. So, now when you have a plotted points, there are many ways you will get mid points. It may be like this, when you have several points like this. So, it can be like this, it can be like this, it can be like this. So, all these things cannot be possible to you can say considered. So, we have to choose one, okay. So, that one must be very best. So, by inspection it is very difficult. Of course, we can make a judgment, but it is not accurate judgment. So, that is how you have to go through statistical procedure only. There is a statistical procedure, that statistical procedure is called as a reliability check. So, that reliability check will indicate whether this particular path is best one, or this particular path is best one, or this particular path is best one. Okay. So, so far as significance of the parameter is concerned, then standard error of alpha, then we have to use T statistic, T alpha head. Similarly, we have to see T beta heads. Okay. So, then since it is issue about the significance, then significance, for significance level we have to compare with the probability level. Okay. So, in this particular systems, so the significance level we usually consider at 1% level, 5% level and 10% level. So, maximum limit we will go up to 10%. Okay, so now 1%, if the some item is significant at 1%, then obviously that means 99% chance is fact and 1% is not supporting. Similarly, if it is at 5%, that means 95% are supporting and 5% are not supporting. Again 10, if we will say 10%, then 90% are supporting, 10% are not supporting. Again in between there are these test procedures are usually divided into two parts called as a one tail test and two tail test. If it is one tail test, then it may be considered as a 1% level, 5% level, 10% level. If it is two tail test, then you have to divide by 2. So, obviously, a two tail test at 1% means we have to go 0.05 and 0.05. Similarly, 5% means you have to go for 0.1 and 0.1. Okay. Similarly, 10% you have to go for 0.5 and 5. Okay. So, this is how you have to proceed. So, that means this particular item is normally distributed. So, this part and this part has to be considered. This is plus side and this is minus side. So, this is how you have to observe. That means 50% is this side and 50 side is this side. So, if it is one tail, then it is a skewed distribution, that is positively skewed or negatively skewed. So, this is how you have to go through it. Okay. So, now, so probability level you have to decide and probability level you have to decide, and with this particular system. So, we have to check the standard best fitted model or reliability model. So, now I am giving you the exact procedure of reliability. What is all about this reliability of this estimated model? So, reliability, so far as the reliability is concerned, reliability of estimated is concerned. So, we have to check two things. Okay. First is with respect to reliability of parameters, and second is reliability of the overall fitness of the model, overall fitness of the model. Okay, overall fitness of the models. Okay. So, first is a reliability of estimate. That means, the initial starting point is you must have y information, x information. Your problem, your basic relationship between y and x must be known to you. Then you have to make a functional relationship, that is what we will call it in mathematical model. Then you transfer into statistical model by introducing the error component. Then you have to estimate the models by the use of Euler's technique. Then you like to have y hat equal to alpha hat plus beta hat x. So, the moment you have y hat equal to alpha hat plus beta hat x, then we are going for reliability. So, so the reliability has two parts. One part is with respect to significance of the parameters, that to alpha hat and beta hat. So, what we have just explained details, and second is the overall fitness of the model. So, the overall fitness of the model is that that can be also standard techniques through which you have to judge the overall fitness of the model. Just like see here there are three parts, alpha plus beta x, alpha one part, beta x another part, and y is another part. So, this is one side and this two part is another side. So, this should be this particular reliability means. So, what is the overall impact of this particular model? So, that is means explained side and unexplained side. Then obviously, the reliability of the individual parameters, that means section A and section B, that is alpha plus beta x is one part and u is another part. So, we like to know what is the judgment of explained item and what is the judgment of unexplained item. Okay. So, reliability has two parts, with that is with respect to parameters significance check, and this is with respect to overall fitness of the model. Okay. So, far as this reliability of the parameter is concerned, so we like to know the significance of parameters. So, that means if parameters. So, since that means if your objective is to check the reliability of parameters, that means the idea is very clear. You like to know what is the significance level of the parameters. If that item is statistically significant and close to 1%, then that the model accuracy is very high. If it is if that item is not statistically significant and 1% at one tail test or two tail test, if it is totally failed, then you have to go for again 5%. Okay. So, now if 5% again you have to go one tail test or two tail test. If it is not significant, then you have to go to 10% level. Again 10% level you have to check it at one tail through one tail test and you can say two tail test. If not after the 10% experiment, if it is not statistically significant, then we can conclude that this particular item or variable is not at all statistically significant. Yes, there is a relationship, but that relationship is not strong enough to use for forecasting. So, that is how the reliability rule is concerned. So, now what is the significance of parameters? Here the significance of parameters, we have two aspects, that is alpha aspect and beta aspects. Okay. So, we like to know what is the significance of alpha head and beta head. For that we have to know two things. Okay. So, alpha head is known to us. So, we like to know T alpha head and T alpha head tabulated value. Okay, tabulated value, and this is estimated value. This is estimated value. Okay, T alpha head and T beta head. So, no, so this is not estimated, in fact this we call it a calculated value. Okay, calculated T statistic and tabulated T statistics. So, now we have to compare the calculated T of alpha head and tabulated T of alpha head. Similarly, you have to calculate or you have to compare the calculated T of beta head and tabulated T head beta heads. All right. So, now what is happening here? So, now this T of alpha head depends upon two components. T of alpha head depends upon the individual alpha head value and its standard error of alpha head. Similarly, for beta heads, so we have two aspects, that is tabulated T statistics and calculated T statistics. The calculated T statistic again depend upon beta head and standard error of beta head. Okay. So, this is one part of the story. Okay. One part of the story, that is what we call is a reliability of the parameters. So, once what is the exact structure of reliability of the parameters? So, we like to know means we must have alpha head value and beta head value. So, we must have a variance of alpha head and variance of beta head. Then we have to get the standard error of alpha head and standard error of beta head, because the square root of variance of alpha head is nothing but standard error of alpha head, and square root of beta variance of beta head is nothing but standard error of beta head. So, now that means we must have alpha head and variance of alpha head and beta head and variance of beta head, then everything will be automatic, means not automatic, everything can be very smooth to get this work done. All right. So, now the second part of the model is called as a reliability of overall fitness of the model. So, this is what we call as a significance, or otherwise it is called as a significance of overall fitness of the model, overall fitness of the model. Okay, fitness of the models. So, overall fitness of the model for a particular econometric technique solely depends upon the statistic called as a R squares. Okay, R square, this is what it is usually depends upon R square. This R square represented as a coefficient of determination. We have discussed R component, that to small r, that is what we call is a simple correlation. So, covariance of x y upon sigma x and sigma y, that is with respect to two variables. In fact, the starting point of correlation is two variables. So, now we must have we must have two variables, then you can calculate the correlation. Then correlation coefficient simply represented as a small r. If you will make it a square, then it is square of correlation coefficient. But for bivariate models, this particular small r and capital R more or less same, but when we will square it r square, that is what we will call it, it is contemporary, it is small r square, but this r square, there is a difference. Okay. So, this is called as a coefficient of determination. This particular item is called as a coefficient of determination. This particular item is called as a coefficient of determination. What is the rule of coefficient determination? The rule of coefficient determination is that so it is the ratio between exponents to total. So, that means what is the percentage of explained component is influencing the dependent variable. So, that is what we will call it R square, that is overall fitness of the model. So, this R the moment there are means two steps here. First is you have to calculate the R square statistics. So, now once you will get R square value, so that R square value has to be tested again, because here we are having y equal to alpha hat and beta hat x only. So, that means alpha hat is known to us and beta hat is known to us, nothing is available here, but lots of other statistics also simultaneously we have to calculate. So, for the reliability is concerned, one part of this particular item is called as a R square. So, R square is the ratio between explained sum square by total sum square. We will derive details in the next class, not today. So, now so this R square structure is like this, means it is the ratio between explained sum by, you can say, total sum squares. So, now so so far as the reliability of R square is concerned, then it depends upon F statistics. Okay. This depends upon F statistics. So, that means for significance of the parameters we are using T statistics, and for overall fitness of the model we are using the F statistics. So, now like this particular case, here also you like to know what is the calculated F and what is the tabulated F. Okay. Calculated F and tabulated F. So, now we have to compare the calculated F with the tabulated F. So, means what is exactly the difference between calculated F and tabulated F, or similarly calculated T alpha hat and tabulated T alpha hat, calculated T beta hat and tabulated T beta hat. So, now the thing is that for calculated there is a standard techniques, or you can say formula through which you can obtain this value. Okay. But there is standard by simulation we have a statistical tables. Okay. So, statistical table has a standard norms. So, now we have a calculated statistics and we have a standard norm. So, we have to compare the calculated statistic with the standard norms. If the calculated statistic is greater than to the standard norm, then the statistic then that item will be statistically significant, but the standard norms are available at different significance level. For instance, at 1% level, at 5% level, at 10% level. Again for one tail and two tail, one tail to two tail, again one tail, two tail, again one two tail. That means with respect to 1%, 5% and 10%. But some of the standard books, there is chance of 25%, they may go also up to 25%. But what hardcore for statistician finance problem or any other technical problems. So, we usually handle up to, you can say, 10% level only, but social science problems which is very complicated, and when your sample size is very extremely high and high, then that times you can go for but very extreme case you have to go for 25%, but 25% is not at all very reliable one. So, the most effective way you have to go up to 10%. Okay. So, if it is not up to 10%, then you have to reject or redesign the structure entirely. All right. So, now for T statistics you have a T tables, and for F statistic you have a F tables. Okay. So, again for T tabulated and F tabulated, there is another items we need to integrate to get this particular item, that is what we call as a degrees of freedom. Degrees of freedom. Degrees of freedom means it is the difference between total number of observations and the number of independent variables represent in the system. So, we will discuss in details when we will go for that. Is what we will call sometimes call it is a n minus k. N is the total number of sample size and k is the total number of variables, independent variables in the systems. Okay. So, n minus k is or total number of parameters in the system, rather instead of variables you can say that k represents total number of parameters involved in this particular model. So, now this n minus k represents the degrees of freedom. So, okay. If the degrees of freedom is very high, then the model accuracy will be very high, but for this is true for this T statistics, but for F statistics we have two different, in fact for this F statistics we have two different component. One is called as a explained sum squares, okay, and another is called as a total sum squares. So, that means there are three standard items. One is called as a TSS, then ESS, then sometimes called as a RSS, or you can say sometimes it is called as a unexplained sum squares, explained sum squares. Okay, so TSS represent total sum squares, which is nothing but actually we will derive from this structure y equal to alpha plus beta x plus u. So, this particular item is nothing but explained sum squares, and u related to unexplained residual sum squares, and t represents to y. Okay. So, this is how the all about the integration. So, but the calculating procedure is something different with respect to total sum square, explained sum square, and residual sum square. So, now when we have a information, so we have y information and x information through which you feed the model, you get the model, but anyway you feed, but when you will go over typically means in a smaller version of the problem, then usually we will not derive every time. So, what we have to do, we have y information and we have x information. So, we know what is alpha head formula and we know what is beta head formula. Similarly, we have also formula for variance of alpha head and variance of beta heads. So, again we through statistics, t statistic, there is a calculated statistic how to get this t value. So, now if you will go sequentially with respect to the available information, then you can automatically or by very easily you can get this particular value, that is t alpha had calculated and t beta had calculated. Similarly, in the case of R. So, now once you have y information and x information for this particular bivariate zeta. So, what you have to do in the first step itself, you have to calculate sum y, sum x square, sum y square, sum x y. Okay. So, now in the same times you must identify number of sample size, that is n, okay, and in the same times what is k. In fact, for this bivariate models k is usually represented as a 2. So, that means the structure is n minus 2, degrees of freedom is n minus 2. K represents number of parameters in the systems, number of parameters in the system or number of variables in this particular systems. All right. So, now this will determine the degrees of freedom. So, now once you have such information, then you first calculate the alpha statistic, alpha head statistic, then beta head statistics. Okay. First you start with actually beta head. So, that is summation x y by summation x square, or if means it is in a deviation format. If you will go by other way around, then it is n summation x y minus sum x sum y divided by n summation x square minus sum x whole square. This is the standard formula. Okay. So, whatever shape of this particular problem, but whether the shape of the problem is perfectly okay or not, that is how we are checking here. So, that is how there is no hard and fast rule that we have to check the functional form or you have to derive etcetera. First you do it, but the best procedure is you check it properly, then you fit the model accordingly, then obviously reliability is very consistent. Or else what you can do, you start with something, then automatically at the point of reliability it will be give you indication whether this model is perfectly okay for forecasting or not okay. Okay. So, now let us assume that we are we have no knowledge about it, all these testing etcetera. So, we start by the standard rules, you get the alpha head and you get the beta head. So, then you fit the model like y head equal to alpha head and beta head x. So, now you calculate the alpha head statistic, beta head statistic, then you go by standard procedures, get the variance of alpha head, get the variance of beta head, then get the standard error of alpha head and standard error of beta head, then you calculate the t of alpha head, calculate the t of beta head, then you compare with the calculated t of alpha head and calculated t of beta head. So, this is the tabulated value available with you, and obviously you have to calculated values. So, then you have to make a comparative analysis. In fact, you go any statistics books or any econometrics books, in the end of the books you will find standard statistical tables with respect to t statistic, with respect to f statistic, and with respect to j statistic etcetera etcetera. But we need only t tables and f tables. But t statistic is easy to understand and easy to pick up, but f statistic is a little bit complicated. Why? Because when we will get R square, then F is the difference in this particular setup, F is the ratio between ESS by TSS. So, now ESS is a standard statistics, and TSS is also standard statistics. So, ES depends upon something, because it is degree of freedom is completely different, and TSS degrees of freedom is completely different. You see here, this is ESS part. Okay. So, this part the degrees of freedom, this part degrees of freedom is okay, and this part degrees of freedom is, because it depends upon two parts, but this is only one part. Okay. So, now since the degrees of freedom are different, so obviously in the case of ESS the degrees of freedom will be completely different, and below TSS the degrees of freedom is also completely different. So, as a result, so in the F case, for F statistic the table is something different. So, that is why you must have thorough knowledge how to pick up the tabulated figure. So, once you get the tabulated figure, then you have a calculated figure, you make a comparative analysis. If the calculated statistic is higher enough than the tabulated statistic, then the item is statistically significant. Usually you start with at 1%, because one statistically significant 1% is the best. If it is not best, then you have to go for 5%, the second best. Okay. If it is not 5%, then you have to go for third best, that is 10%. After that, if that item is not statistically significant at 10%, then the better you have to stop there. Stop means you have to either redesign, or you can say restructures, then again you have to go for reliability test till you get this item significant. But for bivariate structure it is very easy to pick up, or you can proceed, but when you will go for multivariate, it's the problem is very complicated. It is very difficult to get all these variables statistically significant or overall fitness. Obviously, when you will introduce one after another variable, or when you will move from bivariate to multivariate, then obviously explained sum is all with respect to x items, and total sum is with respect to y only. So, obviously, y is always 1. So, that item will be remain constant. So, when we will add one after another item, the numerator will be start increasing. So, as a result, R square will be always high once you introduce one after another variable. So, when R square is exclusively high, then your F statistic will be exclusively high. So, the overall fitness will be usually very high, or you can say you can be get significant, but the parameter you may not get significant. So, you have to make a compromise. So, the compromise rule we will discuss details when we will go for multivariate from R. So, with this today we will stop here, and we will discuss the details in the next class. Thank you very much. Have a nice day.